Hi, so today we're going to study Chapter 11, Competitive Markets and Partial Equilibrium. So this class is basically about the first time we're going to put together both demand and supply in one single environment. Okay, so basically today this is important because we're going to be able to do something more than just maximize utility or maximize profit, but actually we're going to see how prices are determined in a market, okay? When consumers and suppliers come together. So, of course, we're still far away from the study of what's called general equilibrium. So this is basically a special case of general equilibrium, which is called partial equilibrium or competitive equilibrium. So consider a market. This market has I consumers and J firms. There are L goods, so they can be, of course, greater than equal than 1. And consumer as I's preferences are given are basically determined over consumption models and are given by a utility function U sub I. I is the indicator of the each individual agent in this market. And the initial amount of goods that are in the economy or endowment is given by this omega. Okay? So omega is a vector of size L and it's telling you how much you have initially of each good in this market. Okay, so the endowment is very important that you understand what it is. So imagine I'm running an experiment about trade. So I put some individuals in a room and then I want to understand how they trade with each other given initial allocations of goods. So imagine I want to give them apples and oranges, and then then we have two goods. Then the endowment is basically the quantity of apples and oranges each agent has. So if there is a total of 10 apples and 10 oranges, the total endowment, the summation of the omegas for each good is a vector equal to 10 for the apples and 10 for the oranges. Now, the individual allocation omega I of apple and oranges will depend on the experimenter. So he or she will assign different levels of apples and oranges according to the initial conditions of the experiment. So omega I, for instance, can be 6 apples for individual 1 and 4 apples for individual 2. And then the opposite in terms of oranges for the two agents, such that the apples and oranges held in the economy are equal to 10. Okay? So we're going to assume that initially these agents have at least weekly positive quantities of endowments. Now, here we also have firms. So in this experiment, we don't only have two traders, but also we have, for instance, a machine that can produce something like it can actually create juice out of the orange, right? So you can imagine this is a firm that takes as input oranges and then creates as an output using basically creates an output oranges at a cost, right? So the firms may transform some of the endowment of a good into additional amounts of other goods. Okay, so each firm J has available to it their production possibilities summarized by the production set. So here in particular, we're imagining a very general production set. It can actually produce any of the L goods. It can produce, it doesn't mean it has to produce positive quantities. And then an element here, Yj, is a production plan and also is of size L. So important thing here, so both consumers and firms have a vector over L, right? So consumers basically will consume any of these L goods, and then firms may input some of these L goods and create more of other of these L goods, okay? Now, the important thing here is that the net amount of good in the economy is the summation of the total endowment of each good, right? So notice here that we're using a particular notation according to Mascolel, which the omega L is basically the summation over the entries of omega Li over all I in the market, right? So this means that if I sum the endowment of individuals for each good L over all individuals, then I obtain this omega L. So omega L is the total endowment of good L. And I have to add to this the amounts of produce or in basically the firms take as an input for each good L. So therefore, this is the total endowment. Now, as you can see here, the important thing is that we're adding up. So sometimes if your input, this is subtracting. So there is a minus, because the inputs, as you remember from the chapter in production, has a minus sign. So this will, of course, subtract from the total amount of quantity in the economy of certain good. In other words, in this experiment, I can take one orange and it will disappear right from the total amount of physical oranges, and then it will become a new good, which is the orange juice. Okay. So definition. Now, we are interested in what is called an equilibrium, a competitive equilibrium. So in order to understand that, we want to define the first object of this of interest, which is called an economic allocation. An economic allocation is basically a big matrix of consumptions. So this is the vector of consumption from individual one. So this is a vector in RL. And then here you have the consumption of consumer capital I. So we stack them together as columns, so now we have a matrix, right? The rows are L, because we have L goods, and then the columns are I. Now we take this matrix and we put next to it another matrix, which is the vector of production. And again, so Y1 is a vector of size L of all the production plan of firm 1. And then Y capital J is the production plan of firm J. We stack them together, and then this is another matrix of size rows L times columns capital J. And we put them, all of them, in a single matrix, which is of rows L and then of columns I times J. So I plus J. So this is basically a specification of consumption for each consumer and a production plan for each firm. So notice that here this is very general. Now, the allocation will be called feasible whenever the sum over every consumption allocation over each individual of each good L is less than equal than the total amount of physical goods of that particular good L. So in the apple and oranges plus orange juice example in the experiment, so I will have to add up all the consumption of oranges in my experiment, and they have to be less than equal than the total amount of oranges available in the economy. So that means the initial allocation of 10 oranges potentially minus some uses of this as an input. Okay. Now, in the case of the orange juice, so initially in my experiment, I didn't have any initial orange juice. I just have a machine. So therefore, that means that there has to be this omega of the orange juice is going to be 0 because there is no endowment of the orange juice. However, you can produce it. So Y of the orange juice is actually can be positive, and therefore the consumption of orange juice has to be less than equal than the orange juice that you can produce in this experiment. Now, let's define a competitive equilibrium. So the allocation, which is this huge matrix of consumption and production, and the price vector P. So a price vector P is not a matrix, it's just a vector in size L. It constitutes a competitive all-world ratio equilibrium if the following conditions are satisfied. So the first condition is profit maximization. So for each firm J, Yj solves the maximization of Yj in the production set of firm J, capital Yj. It maximizes the inner product of prices times the production plan. Remember, these are profits because when inputs are negative multiplied by positive prices, this gives you the cost. So we have a minus cost, and then revenues are positive prices of outputs times the positive quantities of outputs, which is the revenue. So this is maximizing the sum of revenues minus cost. Okay. Now the price is assumed to be basically taken as given by firms. So firms do not hold market power. So that means they cannot change prices. They take prices are given, and their choice is the quantity they can produce given the prices. Okay, so this is a model of perfect competition. That's why it's called competitive equilibrium. So importantly, firms, when they hold some market power, for instance, a monopoly, then they'll have some control on prices. Here, they don't. Now, utility maximization. So on top of firm's profit maximizing, you also have that consumer utility maximize. So for each consumer I, then the allocation xi in this big matrix solves the maximization problem. So max of x in this consumption space capital Xi according to each individual utility. Each individual agent may have a different utility subject to a feasibility constraint. And here is very important because you will see that the budget changes. So this is a different problem from the problem we saw in chapter 3 in MassQL, because instead of having just income as an exogenous parameter, here income is endogenized. So the main purpose of general equilibrium is to endogenize income. Okay, that is how it differs from the chapter 3 consumer part. So what is the budget that now is endogenous to the market? Is price times the consumption of individual I is less than equal than the total amount of money endogenized in the following way. So if you were able to sell your initial endowment of apple and oranges in my experiment, then I have to multiply by the prices at which they are exchanged. And this will give you the amount of tokens, right, that you can have. But in principle, right, in this economy, prices can be interpreted just as an exchange rate. So it's basically the exchange rate of apple and oranges. So in this market, for instance, you exchange, this is a particular number I'm going to fix, but this can change in the experiment. It can be 1 apple is equal to 2 oranges, right? So now if that's the case, then you multiply basically the exchange rate and you put everything in one single unit. So, but in general, right? So you can think of this as money. So you sell everything for tokens, and then each good apples and oranges have their own price. And now you multiply the omega, which is the physical amount of endowment of oranges and apples, times the price. So you sell it. And then you also take the profits of firms. So firms may produce profits. And now how much of the profits you participate as agent I? Well, so you have basically a share of the firm. And the share of the firm is this theta, which is a weight that is basically a probability. But this is it works mathematically like probability. But in this case, it's just a share. So it's the fraction of ownership of the profit of each individual I of firm J. So what is the total dividends that this household receives? Well, it's the summation of the profits multiplied by the shares held by individual I of the particular firm J. Okay, and that's how you endogenize the income, because now this part here is no longer exogenous. It depends on the prices. So when I'm telling you this is no longer exogenous, because in particular, this definition is really telling you that prices will solve this system of equations implied by maximizing profits, maximizing utility, and finally, with a final equation, which is the market clearing equation, which means that the summation of all basically consumption has to be equal to, and this is exactly equal, to the summation of physical goods as endowment plus the production and net production, so inputting and output. So now together conditions 1, 2, and 3 will form a nonlinear system of equations whose unknown is which has a sole unknown, which is the price vector of psi. So basically you will solve this given endowments, and then you will recover the prices, and then you will recover also the consumption and the income level. So what are the primitives of this system of nonlinear equations? So what you have to know here is you have to know the production set, and you have to know the preferences, okay? Of course, you have to also know the ownership structure, the theta. Then if you know all of this, you can find a price and then basically the allocations of X and Y. But remember, so in the end, as we progress through the chapter and through this section of our class, we're going to refer as the equilibrium as the price vector only. Why? Because once you have the price vector, you can input it into the problem of the firm and obtain, by maximizing profits, the supply, which is all these vectors yi, yj. And then you can do the same for the consumer problem. So in other words, once you know the price, then given that you know already the utilities and you know the production set, then it's immediate to compute the allocation. So we're going to refer basically generically as the equilibrium as the price vector, okay? But mathematically, we solve a nonlinear system of equations to find the allocations and to find the price, given endowments, given utilities, and given production sets, okay? And of course, this maximization hypothesis. So profits maximize, profits are maximized, utilities maximized, and the market clears. This is the definition that creates the system of nonlinear equations. So this is the mathematical problem. So now economically, we're studying now supply and demand, okay? So the fact that each firm maximizes profits, this will generate a supply and individual supplies. And then when I can aggregate them together, and this will generate in the market clearing aggregate supply. Now, aggregate supply also has to take into account initial endowments, right? So initial endowments or physical goods in the economy. And all of this here then is total supply, okay? Now here you have instead consumption, right? So consumption is again generated by maximizing utility. And once you have that, then you compute aggregate demand. So aggregate demand is equal to aggregate total supply, okay? So now we need some preliminary results. The first result basically is telling that we're going to reduce notation here. So the allocation, remember, this was this huge matrix of rows L and columns I. Now it becomes matrix X. And then Y the same, so it's just Y is the matrix. So now together, this is this bigger matrix that I described before. This is the allocation. And then you have the price that now is going to be positive, strictly so. This can be ensured under some mild conditions on utilities and profit and production sets. So we're going to declare that this positive price constitutes a competitive equilibrium. Then it follows that also the allocation xy with a different price, which is the original price multiplied by a scalar alpha, is also a competitive equilibrium. Why? Basically, this is a consequence of the homogeneity properties of production and utility maximization. So that means that we can always normalize the prices and fix one of the goods as one. So usually this price that I choose to normalize its price to one, it will set the units for the rest of the economy. So in this experiment, I told you that you can think of prices as exchange rates. So if you have you have this set of three goods, you have to tell me what is the exchange rate from one apple. Basically, it means two oranges, and then one apple means only one orange juice. So that orange juice glass. So that means that these exchange rates constitute a price, and this is the normalized price because this is telling me everything in terms of apples. So in that case, the price of apple has to be set to one. Okay, that's what I mean by being able to normalize one of the goods, the price of that good to one without loss of generality. This is a consequence of homogeneity of degree one, okay? Of degree 0 of the utility and degree 1 of the profit. Okay, so now, so we have this lemma, the first result. So if the allocation x and y and the price vector p, which is strictly positive, satisfies the market clearing condition, that is the third equation, which just says that aggregate supply is equal to aggregate demand for all goods different from a particular fixed good K, and if the consumer's budget constraints are such that you actually satisfy Walras law, so you hit the budget constraint with equality instead of inequality for every individual, then the market for good K also clears. So this means that, again, a consequence of the homogeneity properties is that if I'm solving the system of nonlinear equations before, I have to solve it for each of the market for each good. So you have L goods, and all of them constitute a market. So now all of these markets will have its corresponding price, and then according to that price, you will have that aggregate supply of that good is equal to aggregate demand of that good. Now, if I check these conditions, the market clearing conditions for all of the goods except one good. Say, for instance, I never check the condition for the apples market in my experiment. Then just by checking the market clearing conditions of the oranges, physical oranges, and orange juice, then I am sure that the final market, the apples market, also clears if the two previous markets clear. In other words, it means that I can take my system of nonlinear equations in the previous part and then always reduce one market, okay? These are nice results for computational reasons, but also tells you of the nature of our system of equations. So because of homogeneity properties, this is an over-determined system. So there is always one redundant market, okay? And because of that, you can never pin down exactly prices in the sense of absolute levels. So prices are only exactly determined by the system as relative prices. So again, you understood, I hope, from the previous chapters that rationality basically requires only knowing relative prices, okay? So in particular for interior solutions, the utility maximization problem is such that the marginal rate of substitution is equal to the ratio of prices of any two goods. The same is true for the profit maximization problem, where the marginal rate of transformation is equal to the ratio of prices, okay? Now, this, of course, with interior solutions. So this should give you an intuition that the only thing that matters for people to maximize is basically the ratio of prices. And this confirms this intuition in a more formal way, okay? Now, so this is still too general for what we want to do today. Eventually, we're going to go back to this very general definition of the competitive allocation. But now we need to understand a simpler version of this very difficult problem. And the simpler version is basically a model where I'm going to restrict utilities in a particular way to simplify this system of equations. And this model has a lot of interest in applied work. So this is called partial equilibrium competitive analysis. And the heart of this model is basically consumers are assumed to have a particular kind of utility. So they cannot have general utilities. They're going to have what is called quasi-linear utilities. And we have also more structure. So right now, just for the simplicity of this class, we're going to let the economy only have two goods. So it's not now anymore the capital L goods, which are very general, but now we go to something specific. So there is only two goods. The first good L, basically, which is going to be denoted by X, and the subscript I tells me the individual consumption of such a good. And then the second good is number M. So M is going to basically be the second good, the quantity level consumption of that good. And MI is the level consumption of individual I of such a good. It's called the numerator because we're going to fix its price to 1. So everything is going to be measured in terms of that good. Now, each consumer has a quasi-linear utility. Basically means that the utility of each individual over these two goods, MI, the quantity of M and the quantity of X, is equal to the following function, which is mi plus phi, which is potentially a nonlinear function of the consumption of xi. So it's quasi-linear because it's almost linear, right? So the first part is linear, but the second part is not, okay? So usually this is the structure of a quasi-linear structure, right? So we have that anything, we have only one good that enters linearly, and then the other good enters non-linearly. So in particular, quasi-linearity can be generalized, and I can make X no longer one good, but actually a vector. I can have, say, L minus one goods, but the numerator is the part that enters linearly the utility. Okay. Now, so I want you to think about the units of the utility. So usually we learn chapter 3 that utilities in the most general version are ordinal. So they don't have any units. They only contain ordinal information. But the quasi-linear utility is different because this one actually has some cardinal information in it. In particular, I want you to think of the units this is measured on. So given that M, which is the consumption of the numerator good, enters directly, that means that the utility here is measured in terms of some transformation of the units of the numerator good. So if the numerator good is, for instance, apples, right? This will be measured in terms of basically of units of apples. Okay, but in particular, the numeric good is thought to be a composite good. So usually it's thought to be remaining money you have that you haven't spent on X. So in that sense, the quasi-linear utility, the most common interpretation is that it's measuring money. Okay. I'm not gonna dig a little more into that, but I also want to remind you that we have the expected utility case, which also has some cardinality properties. So, but think of then of this quasi-linear utility as cardinal. And this structure will be very useful because it will basically mean that the consumption of the interior good X, which is the non-numeraire, will depend on prices, but will not depend on income. So this will simplify the problem a lot because I will be able to create a system of equations that doesn't have to deal with income effects. Okay, so it's only going to depend on prices, and then the numeraire good is going to capture all income effects. So remember that a usual demand, as in chapter 3, has prices and income effects. Now, in this particular case, using the quasi-linear specification, we can make the non-numeraire part of the goods that are non-numeraire, they will depend only on prices, but not on income. And the numeraire will depend on income and prices, therefore capturing or somehow absorbing all the income effects. Now, so the consumption set here, as I said, is basically, in the most general case, this multiplication of the numeraire good times L goods, right? L goods are corresponding to the non-numeraire goods. So now this function phi I is bounded above and twice differentiable, such that basically you have, in the scalar case, that when you have only one good, L is equal to 1, you have that the partial of this phi function is always positive, so that means more of the consumption good X means more utility. But then the second derivative is strictly less than 0, so this means that it's strictly concave. So this is marginal decrease in utility. And this happens for all positive quantities of X. And also, we're going to make a normalization. That means that if you consume 0, then your utility is 0. So this normalization is important in terms of units, but you can also set it to a different number. But here we're going to use it actually to make sense of the solution to this implied system of equations in the competitive equilibrium associated with this quasi-linear utility. So the numeraire M is a composite good of all other goods. So basically, you can imagine that M will capture all the outside options of not purchasing the particular interior good. So to make it more specific, right? So now we're going to stop with the experiment that I told you to have in your mind. Now we're going to switch to a more realistic kind of market and to a more realistic application. So many people may be interested in a particular market. For instance, say that you're hired by Walmart to study the market of cereal. So people buy cereal, and you want to try to understand the consumption and supply of cereal, kind of isolated from the rest of the economy, right? So now, in that sense, you would like to basically go and try to understand the market in isolation. So as long as we understand the market of cereal as basically being the market of that only depends on prices and not on income, so it doesn't have these features of inferiority or as an inferior good or being a superior good, a normal good, then you're fine. In the sense that so most people are gonna buy cereal more or less in a broad range of income. So therefore, you can kind of think of cereal only changing with the price change and not with income, right? So in that and another way to see it is basically what fraction of income buying cereal represents. And usually this fraction will be small in terms of the total income that you get in a month or a week. So that means that you can, this is kind of an ideal setup to study the quasi-linear equilibrium, in the sense that you can abstract from away from income effects. Okay. Now, so in that sense, in the serial example, then the numeraire is basically all other things that you can purchase with your money that are not serial, right? So this is the outside good. And then therefore it can actually be thought as this composite good, which you can think of an average of the rest of goods. So the key idea here is that xi is small relative to the whole expenditure and thus has no well effects. Or they are close to null, so we can approximate by this model. Now, we can normalize the price of numeraire to 1, and P is the price of good L. So the numeraire, remember that the idea is that we are going to fix its price to 1, therefore making everything measure in terms of units of the numeraire. We usually can think of it as money, given that this is a composite good, okay? And now each firm J, from 1 to capital J, is going to produce good L from the numeraire. So in this abstraction, the idea is that firms, remember that M is a composite good, so it contains all other goods that are not serial, right? So now, of course, in this abstraction, we can imagine that firms take some M, which is this amount, of composite goods, and out of it, they produce a unit of serial. So, and in other words, what you say is that there is a monetary cost, that is the units that the numeraire is measured on, to produce a unit of serial. So a box of serial costs Cj, right? And then 2 boxes, then you use this function, so C of 2. And basically this function is telling you how much of input M do the firm J needs to produce quantity Qj. And this changes with the firm, so it's subindexed by J. And remember here, we're going to assume that production is efficient, and basically the numeraire is 1. So remember here that usually the cost, as we studied in the previous chapter, was a function of the output, conditional on the price of input. But the price of input here is equal to 1. So it disappears, right, from the cost function. So the cost function now becomes only a function of Q. Important thing. Now, the intermediate or demand of M of the firm, so this is, remember, the factor demand of the firm, is called Zj. So we are using a different letter, because this will tell us the consumption of firms of the good of the numeraire, right? So consumers can also eat some of the numeraire, right? This is a composite good. Any other thing that is not a serial. But of course, firms can also use it as an input. So this will be captured by Z. So then what is the production set of the firm? So they use as inputs minus Zj and produces Qj. Okay, Qj is positive, Zj is also a positive quantity, and then this greater than equal. Remember that in this notation of the cost, we make Z actually positive, such that when you use the production plan, you have to put a minus in the front. So now how is the technology captured? So this is given by the cost function. So that means that prices multiplied by the quantity is greater than equal than the cost evaluated by quantity comma the price. But because the price is equal to 1 and this all of it is a scalar, then I only have that the input is greater than equal than the cost. Okay? So this is the feasibility. Of course, efficient firms will produce exactly when at the boundary of the cost, right? Now the cost function we're going to assume is also twice continuous differentiable, and then we're basically going to assume the production plan is the production set has non-increasing returns, and in fact has strictly decreasing returns. So the first derivative says that more quantity gives you more input, more numeraire gives you more quantity. So the first derivative is positive, but then the second derivative is also positive, which means that this cost is basically a concave function, okay? So concave cost is equal to decreasing returns. A strictly concave cost is equal to decreasing returns. So, and that means actually that concave cost is equal to a strictly convex technology. So the convex set, the production set is convex, okay? Remember, so convex set, the production set means concave, basically means concave cost. Now, we assume that there is no initial endowment of good L, and basically consumer's initial endowment of the numerator, omega of the endowment, so therefore sub m of each individual is positive always. So total endowment is the summation across individuals. Got it? Now, importantly, right, we have that the allocation, the partial equilibrium allocation now can be simplified a lot, mainly because of the quasi-linear structure. So remember that we can check just one mark out of the all markets. We can check L-1 markets, and if they satisfy the conditions of the partial competitive equilibrium, then the final market is fine. So here we normalize the price of the market of endowments, of the numerator as 1. So that is the market we're gonna take out, and then we're going to only focus on the interior goods. In particular, for the case of one good, is going to be of the market of X, the consumption good. So now, if firm's profit maximize, what does it mean? It means that cost is minimized. And if cost is minimized, then you actually write the first order conditions allowing for interior solutions. Then it has to be that price is less than equal than the marginal cost. In particular, you have interior solution, it means that price of the good X is equal to the marginal cost of producing Q quantity of this good. With equality, as I said, when Q is positive. Now, and this has to hold for each firm J, okay? Importantly, this is an heterogeneous problem, so each firm J may have different costs. However, because they're price takers, it has to be that each firm, whatever their marginal cost is, possibly heterogeneous, when evaluated at the Q that they produce, that can also be changing across firms, has to be equal to a single vector that is not indexed by J. So price is common to every firm, okay? So that's the important thing about the partial competitive equilibrium. So prices is not a personalized price. So prices are the same price faced by every firm and every consumer. So price basically works as a coordination device. So it's a number in the market that allows every firm to know what they should produce, right? So, and in fact, when maximizing profits, given the price, they are going to produce QJ, okay? Such that they satisfy these inequalities, and with equality when the quantity is strictly positive. Now, what will consumers consume? They will consume according to utility maximization. So if I maximize the quasi-linear utility, then the first order conditions of this problem, given the assumptions that we made, the necessary and sufficient condition for maximization of the consumption of the good X, the interior good, is basically that the marginal utility of X is less than equal than price, and then equality holds when the quantity consumed is strictly positive. So that means that marginal utility of consumption is equal to price. Now, now this is very cool because every firm is maximizing the profits or minimizing the cost given the price P, and then every consumer is utility maximizing given the price P. Notice something. In the original definition, I had a budget. Here, there is no budget anymore. What happened? Well, basically, what means in the quasi-linear world, that is where this helps a lot, because given that all the income effects entered by Walras law on the consumption of the numerator, then I can basically ignore the budget in the consumption of the non-numerator goods. And then the consumption of the non-numerator goods are completely determined by first order conditions. So basically, by solving these first order conditions here, I can determine completely the consumption of the non-numerator goods. And therefore, for this market of the non-numerator goods, then I don't need a budget at all. Now, the final equation, of course, is market clearing. Market clearing means that aggregate supply is equal to aggregate demand. Another feature here that simplifies the problem is that there is no endowment anymore. So the assumption I made is that there was no initial endowment of the consumption vector. There was only initial endowment of the numerator. So because that enters in the numerator's market, I can ignore it here in this market. Because there is only two goods, then this very simplified problem actually solves the whole problem. Now, I have to remark that here you need less information, because you don't need, for instance, knowing the shares or properties of each individual I on the profits of firm J. So I don't need to know the theta ij, okay? I don't need to know the quantity of the endowment of the numerator. So potentially, because I don't need to know how much people consume of this numerator, right? I only need the cost function and of course the utility function of the non-numerical goods, and that's it. And now this model is actually the model you learn in undergrad, right? So this is the famous cross of the supply and demand. So basically what you're doing here is that the marginal utility for the one good will look like a decreasing curve because of the slope that we mentioned, right? And the marginal cost will be an increasing slope, right? Now, this together, right, basically means that you have here some point in the middle that will be an intersection under continuity assumptions. And then this intersection will produce basically a price and a quantity. Okay, so this is basically a competitive equilibrium, right? This will clear the market. So remember, this thing here are basically the sum over all the individual marginal. So here I'm assuming just one consumer and one firm. Now, of course, for graphical purposes. Now, in real life, I have many consumers and many firms. Okay, so I cannot draw this at least with the simplicity I just did, because I have to draw I curves of I supplies and then add them up. On the other, we can also do that, right? So in sum, the important thing here I may mention is that these xi, are basically aggregate demand. So this is the system of equations. What are the unknowns? The unknowns are the x, the q, and the price. Okay, and then x and q are such that they clear the market. Okay. Now you will have a problem set about how to solve this in reality, in real life. But this problem basically is the problem of supply and demand. Okay, so you're finding the intersection of aggregate supply with aggregate demand. And if you find such an intersection that may actually not be unique, then you found yourself a price. And the price, given that you know it, you will be able to solve all the consumption vector and all the production vector. Now, let's learn a little bit more about this mathematical problem. So this problem that I just wrote is a system of equations of how many equations. So, well, it's I, number of individuals, plus J, number of firms, plus 1, market clearing. So you need I equations to determine the consumption levels, J equations to determine the production levels, and 1 price. So the I equations that I mentioned here are these marginal utility is equal to marginal price. Okay, how many of them? Capital I. How many of the equations determining supply? Capital J. And 1 market clearing condition. So this is the 1 equation here. So this is actually potentially a very large system, right? So in particular, solving this can actually be daunting computationally if the market is very large. Now, as I said, what happened with the remaining good? Well, the remaining good is the numerator that I know by the previous theorems, and because of the Walras law here, that it will be completely determined once I know the solution to this reduced system that I just solved. So let's actually compute the equilibrium consumption of the numerator, given the solution to the problem that I just described. So Mi has to be equal to the omega I, which is the physical amounts of goods in the economy, plus, here I have to know the theta ij, which are the shares of profits, and then I have to actually compute profit. So this is the price of the output, so P times Qj, minus the cost of the output that depends on the quantity Qj. This creates the profit of the firm, right? And then here, of course, you basically subtract the amount consumed of good, that is not the numerator, times its price. Now, notice that if I know prices, then I immediately know the Q of equilibrium, right? Because Q was determined from the previous problem. So Q is known, P is known, Xi is known, and omega and theta are primitives of the problem. So now Mi is completely determined. Okay. Now, what is the other thing that I need to solve to have the full solution, right? Is I need to have also the factor demand. So how much of the numerator is in sum or is actually used by the firms. And this is just, in this case, because of efficiency is equal to the set J is equal to the cost level. Remember, numerator is measuring money. So of course it's equal to the cost level, at the level. Now, one of the first problems that we like to tackle in this mathematical problem is to know whether there is a solution to such system of equations. It can be the case that you don't have a solution. So then I will ask you, right, why is it important to have a solution to this system of equations? Well, from a modeling perspective, it's important to have a solution because if you don't have a solution, that means that your model is not internally consistent, right? So it would be nice if you're modeling an economy that at least you can produce a prediction. And you can produce a prediction if you're internally consistent. So lack of existence of equilibrium will lack internal consistency. Now, basically, this is the practical approach. Now, imagine that you actually believe this system actually is mimicking some reality in life, right? So you're actually thinking of a decentralized system and trying to model how people can use a signal, basically a coordination device such as a price, to be able to come up with production and consumption plans and clear a market, right? So in that case, you will also like to prove existence because then that will show that at least this toy version of the world as a model can produce an allocation that actually solves this difficult problem of decentralized consumption, decentralized production, and market clearing. Okay, so now for this particular model, that is the very first model we study of equilibrium, the answer is actually very simple, and the conditions required for existence are also very simple. Now, remember that the problem of existence of an equilibrium is a hard problem that took a lot of years to solve by and really smart economists to solve. And they actually won the Nobel Prize for it. So Arrow de Breu. But here, the very first version of this problem is extremely easy. And basically we say that as remember that these phi's and c were continuous functions. So that's the first thing we need. But then basically what we're asking is that we need an intersection of the aggregate supply and the aggregate demand. And so besides these conditions on the derivatives, I also want to, due to continuity, so it's more important that I define that the max of all individuals of the marginal utility of each individual I evaluated at consumption 0 is strictly greater than the minimum of the marginal cost evaluated at quantity 0 over all firms. If that's the case, basically you can ensure that demand, at the quantity 0 is below, is above, sorry, supply. So in that sense, given the derivative behavior and the continuity, they have to eventually intersect. Imagine this is not the case, and then basically you will get yourself a disturbing possibility. Basically, we can get the following. So basically you have this demand and supply curve, right? And now your demand can be going always down, but then your supply can be going up. So this is of course the cost, marginal cost, and this is marginal utility. So this is a counterexample, right, of the condition I gave you. So therefore there is no equilibrium. And why is that? Because even if these things are continuous, have the correct derivatives and so on, at the very beginning, when quantity is 0, then you have that demand, which is the phi prime, the marginal utility, is always below supply. So they will never cross, at least in the positive part of quantities and prices, okay? So that means there is no equilibrium. So let's go back to the math. So again, so what I'm requiring is that the max across all individuals in quantity 0 of the marginal utility is strictly greater than the minimum cost. And then if that condition holds, given the continuity, given the derivative behavior, supply, aggregate supply and aggregate demand will cross. Now, so this means that actually there is an equilibrium. So existence here is, as I said, is extremely easy. Now, when you generalize this model and depart from the assumption of quasi-linearity, things get fast really complex. So they get really complex really fast. And so we will study that in the following chapters. But now we will focus on this part. But now we have done actually something remarkable that is showing that this large system, potentially large system of equations has a solution. Now, observe that the partial competitive equilibrium definition, as I said, the advantage of this definition is that it does not involve endowments of the ownership share of consumers. This is a consequence, again, of the quasi-linear preferences and the defining feature of partial equilibrium analysis, because that means that if you're an apply guy and you're studying the market of cereal, you don't need to basically know the shares of each consumer of each of the possible. So you don't need to know the stocks positions of your consumers, of the people that go to Walmart or to go to Costco. And you don't also know, you don't need to know how much they earn, right? Their income. So that's actually very useful, okay? Now, not every market can be modeled with a quasi-linear model and with a partial equilibrium model. In particular, if you are going to think of general equilibrium in terms of buying a house, so of course income is going to affect your decisions in terms of buying a house, okay? But buying cereal, you're buying ramen, and so on, this can be thought without, without income effects match under certain circumstances, okay? Now, so we're going to continue now with the existence of partial competitive equilibrium. So this is just going to formalize the discussion that I had before. So assume that this max of the marginal utility of individual over all individuals I, or at quantity 0, is strictly greater than the minimum of the marginal cost over all firms, of course, of the quantity 0. Then there is always a price. Now we're going to denote with a star, such that this is a solution of this system, and basically an allocation of consumption and production, XQ, that satisfies the condition of the partial competitive equilibrium. Okay, so let's prove it. Let's formalize our intuition that the lines cross, right? So we first notice that to find price P star, we only need to find that P at which aggregate supply is equal to aggregate demand. So in other words, notice that to find prices, you don't need individual information. You just need to aggregate supply and aggregate demand. And then basically you go to the market clearing condition and you solve it. So in particular, we're going to call implicitly X star as being the aggregate demand and Q star as being the aggregate supply. And then this gives you a system of one equation with one unknown, which is price, and you solve it. Now, under these assumptions, basically at any price that is greater than or equal than the max of the marginal cost evaluated at 0, we have that the consumed quantity at that price is equal to 0. And that means that the produced quantity is strictly positive. So there is a production surplus. Similarly, say now that price is less than the minimal. So basically here, you have firms that have facing a positive price, right? And then you have consumers that they basically their marginal utility is less than the price, so they don't consume anything. But firms want to produce it, of course. So there is a supply surplus. Now, if you have now the opposite case where the price is less than or equal than the marginal cost, so firms want to produce. Firms don't want to produce because it's actually too costly for them. They are going to lose money. But of course, consumers will want to buy. Then the existence of an equilibrium price basically will be inside this minimum of the marginal cost at 0 and the maximum of the marginal utility. And this, basically, the existence of such a price in such an interval follows from the continuity of the aggregate demand and the aggregate supply. Why this aggregate supply and demand are continuous? Because this is the sum of continuous individual demands and individual supplies. And they are continuous because the phi and the c functions, so the marginal, the utility and the of the non-numerator and the cost function are also continuous. And now notice that aggregate demand is strictly decreasing for all prices according to our assumptions, such that for all prices that are less than equal than this, max over I over phi I at 0, and Q, the supply, is strictly increasing for all other prices. So after finding a P star, the individual level of consumption, right, which is the X star evaluated at the demand function at the price, which is the solution to the problem, and the individual level of production is given likewise by the Q star Qj. So what I'm telling you is that, so under these conditions, aggregate supply and aggregate demand cross at least one time. So it doesn't mean there is uniqueness, by the way. So we only have here a solution. So one of these intersections give you one price. And now, given this price, you go back to the conditions here in the system, and then you solve individually the individual consumption, equating the individual marginal utility to the common price. And you do the same for firms. You equate the individual or heterogeneous cost to the common price. And then you obtain the allocations of Q for supply side for each individual firm, and then Xi for each individual consumer. So this gives you, again, the solution to this is a price, which is now a scalar in this particular example with one good that is non-numerator. And then how many allocations? You have a vector of size I, the consumptions of this good by each individual, and then the production of this good by each firm. So a vector of size J, which is the Q. Now, okay, so now this is cool. Now we have a working model. Now we need to understand what to do with this model. And in particular, this model has been used to show something very interesting about decentralized systems in these economic setups. Basically, it means that if you have this common coordination device called the price, so this common exchange rate, then people will reach something called the Pareto optimality. So Pareto optimality basically means that, I'm going to define it right now, but it is a very nice property of systems that tells you that you cannot improve this system in a clear way. So a Pareto optimal allocation is a feasible allocation of consumption and production, such that there is no other feasible allocation, important feasible, right? Prime, X prime and Y prime, such that utilities are greater than equal better according to the allocation X prime for all individuals. And then there is at least one individual for which these inequalities are strong. So at least one individual improves strictly and the rest remain at least the same. So if that happens, right, then your initial allocation wasn't Pareto optimal, because there is another allocation that can actually improve the lives of one individual, at least one individual, while leaving the others the same. Now, Pareto optimality means that the allocation I have at hand doesn't have any other allocation that dominates the current allocation at hand, the XY here, in the Pareto sense. So I want you to understand this. So I can define a ranking called the Pareto rank, where basically ranks allocations in terms of basically this particular ranking. So it tells you that allocation X prime is better in the Pareto sense than allocation XY, whenever for all individuals the UI of Xi prime is greater than or equal to U of Xi, and for some individual U of Xi prime is strictly greater than U of Xi. This is a strict relation, so this will make the allocation X prime strictly preferred in the Pareto rank to the allocation XY. Now, Pareto optimality means that the allocation XY is such that there is no allocation that is feasible in the economy, that Pareto dominates it, okay? So it's a notion of a maximum. But this is an important maximum because this maximum is not at the individual level, it's at the social level, okay? So now, here comes one of the main results of econ, right? Which is the fundamental welfare theorem. So the first fundamental theorem of welfare economics basically tells you that in this partial equilibrium situation, if the price P star and the allocation XQ constitutes a competitive equilibrium, then this allocation is Pareto optimal. So I want you to put this in perspective. So what we're saying is that you have I individuals, so it can be hundreds of individuals. I have J firms, hundreds of firms. If they're given a number, which is the price, right? So this is an exchange rate of numerator to the consumption good. You say 1 to 3. Then if you give them this number, then everyone will see this coordination signal and say, okay, I can now decide to maximize profit, therefore minimize cost as a firm, and then give you my supply and take it to the marketplace. As a consumer, I say, okay, give me the price. Now I equate my marginal utility of this consumption good equal to the price. And then I know how much I'm going to demand. So I go to the marketplace with my intention to buy this quantity. And then in the market, magically, right, the aggregate supply and the aggregate demand coincide at this number. So now this is a decentralized problem. There was no communication among these individuals. There is basically one single coordination device that is told to everyone. And then at this particular price, everyone magically not only maximizes, okay, but also clears the market. So why this is Pareto optimal? Well, so we're going to prove it, but intuitively, so remember that by definition, in an equilibrium, given the price, every firm, first of all, the allocation has to be feasible. But second, it comes from utility maximization and profit maximization. So in that sense, utility maximization is built in. So this allocation will be such that it's maximal in all feasible allocations, right? So now let's prove this formula because the arguments are a little more subtle. So imagine right now that instead of having the decentralized problem, I replace it by a central planner. So this is, supercomputer takes over and then now wants to reach the bliss point of this society by basically making everyone the happiest possible. So the central planner wants to maximize total welfare. So because I have cardinality here, this makes sense for this central planner to create the maximal surplus possible, which is the objective of this central planner is basically the sum of the utilities for all individuals minus the cost of all firms. So the surplus will be this difference, right? And then there is, of course, the physical amounts of the goods, omega m. So the surplus, you cannot really change the omega m, this is given, but you can change the allocations, right? So now if this central planner wants to maximize surplus, this will create individual consumptions and then the individual productions, subject, of course, to these technologies captured by C and by the preferences captured by phi. So all of this is information that this central planner supercomputer has. So they were able to get it. This is a very strong assumption, but this is a fictional problem, right? So I don't care. The fictional planner has information about preferences and production. And now wants to maximize surplus. And what is the control function, the control variable? So is the quantities x and the quantities q. Now, what is the constraint of this central planner? Well, you have a feasibility constraint. So it has to be that aggregate supply is equal to aggregate demand. So remember, aggregate supply captures all the technological constraints, and aggregate demand is the wishes of these individuals. So now the term, right? So the allocations have to add up. So now the term, so this is not aggregate supply equal to aggregate demand. It's just the budget is the balance of the economy. So whatever is consumed is equal to whatever is produced, right? So now the central planner solves this problem. And now basically any point here will be, any solution to this problem will be a Pareto optimal, right? Notice that due to the nature of our problem, then any allocation that solves this problem is Pareto optimal because there is no way to improve it, right? Because any other allocation won't be maximizing the surplus. So there will be some, if you are not a solution to this problem, then there will be some surplus to be created, and therefore someone can improve. Some individual can improve. So therefore, a solution to this problem has to be Pareto. Okay. Now, so let's solve this problem. And now, basically, this is a calculus problem. I assume differentiability, and then I have a I have a constraint, a balance constraint. I create a Lagrangian multiplier for it. I maximize it with respect to each control, xi, qj. And then turns out that, look at the first order conditions of this problem. So with respect to the Lagrangian, which is a scalar that enters with this constraint, you have mu less than or equal than cj prime, which is the marginal cost at qj quantity. And then you derive this part here, which is the phi I prime, which is the marginal utility of xi, less than or equal than the mu. Because remember, this is the Lagrangian multiplier. This part enters positively, so here mu enters with a positive sign, but here with the q enters with a negative sign, so you have this flip inequality. And now notice that it also has to satisfy the constraint. So the summation of xi is equal to the summation of qj. Now notice that the Lagrangian multiplier in this problem has to be a positive variable. So that means that if I let basically the price be equal to the Lagrange multiplier, then this becomes a partial competitive equilibrium, right? So that means that the partial competitive equilibrium satisfies the further conditions of the central planner. Okay? Now, moreover, given the convexity assumptions we have made, the further conditions are also sufficient. So we conclude that the partial equilibrium allocation is Pareto optimal. In fact, is maximizing surplus. Now, think about this conclusion for a second, which is very important, is that we basically decentralize a very hard problem that require a lot of knowledge. So this central planner, this fictional planner, had access to knowledge about preferences and technologies in a very detailed way. It also had access to all information about omega, which is the physical amount of goods. So this is a huge amount of information, right? So if this supercomputer with all computational power and all information was to solve the problem of maximizing surplus and making everyone the happiest possible, then it will come up with a solution in terms of these first order conditions under convexity assumption and differentiability that corresponds to this set of system of equations. Now, there is a Lagrangian here, mu, that turns out that can be identified mathematically one-to-one with a price. So that means that if instead of having this super planner do this job, I can then just basically go to the market and ask each individual and each firm to maximize their profits and maximize their utilities given a price. So now imagine here comes a mechanism. You need to actually do this. So you create, instead of this supercomputer, you just create a device that says this is the price. So this is the price at which you can exchange things. So do your thing. So maximize profits and maximize utility. And then given this price, then everyone will solve the problem optimally, and then you maximize profits. So now, again, this is not a model of how prices are formed, okay? So this is just an abstraction that tells you that if there is a price that solves the system, right, then now you have this famous Pareto optimality, because this in fact corresponds to the solution of the problem of a central planet. Now, we haven't tell you how the price comes to be. So the fact that price solves the system of nonlinear equations doesn't tell you how the price is realized in real life. So now, luckily for us, so now in modern times, we have marketplaces that are synthetically grown, and then we can understand a little bit more easily how prices are formed. So one example, for instance, is Uber, and basically it's app. So you have basically a signal, which is the price, the fare suggested by the system. And at this price, you have basically drivers that will go to a particular location. And then you have also consumers that will try to grab a cab. So in particular, in the end, you have that the aggregate supply of cabs will be equal to the aggregate demand of rides in a particular location. So if you have surplus of cars, what happens? So you basically reduce the fare, and then that means more consumers are willing now to come in to grab cabs, right? And then less cabs will come, so therefore this will reduce the supply, and then it will increase the demand, and eventually you reach an equilibrium. So what Uber does is basically a problem of trying to be changing the price such that eventually you reach equilibrium. Okay, so they are solving this problem in a very simple way, in a heuristic way. So they are not maximizing the aggregate surplus, right? Basically, they are kind of using the price to try to let each individual and each cab driver maximize their own thing. Okay, and they will at this price eventually reach an equilibrium. But notice that in this setup, you can use the information about surplus of cabs or the surplus of potential riders to be able to calibrate the price, okay, such that you eventually are going to to clear the market. Now, in other marketplaces, you need actually, repeated iterations or interactions to be able to reach an exchange rate that basically clears the market. So we're thinking that this process is already done in some way, and then eventually you already have a price that solves the system of equations. And then, this solution to this problem turns out to be the planner's problem. This sounds very complicated, but the surprising thing is that actually if you let people exchange, they will get close to the market behavior. Well, at least that's the claim. So this is a strong claim. I don't want to say that in real life we have competitive markets. There are markets that a lot of people claim are very close to competitive, right? But again, I will say, for instance, that car riding is very close to competitive. And a lot of people have studied this market using that idea. And I think actually data fits very well the competitive model, okay? So even without Uber, right? So you can think of the market of taxis in New York. So there is a lot of cab drivers, a lot of potential riders. And then there is some way price is fixed, and then eventually even modular regulation, right? And then eventually there is a market that clears, okay? So again, real life markets are way more complicated, but the important thing here is that we've proven something remarkable. That is that you can have the centralized system solving really hard centralized problems, making everyone the best possible in the sense of Pareto. Now, Pareto means that there is no waste and that you cannot improve the situation of anyone, right? In the sense that basically you cannot go and improve the life of one person without making one other person worse. Now, this is under a very strong idea that, as we will discuss later with more depth, that basically there is no income effects, right? In markets, when there are income effects, then you have issues about redistribution. So for instance, can you redistribute $1 from the richest to the poorest? And therefore the poor guy will actually enjoy more this dollar than the rich guy, right? So this involves a cardinal statement and also involves income effects. So here we have cardinality in the partial equilibrium world, but there is no income effects. So this problem makes no sense. We can actually, because you can change endowments, exogenous, if you are a government, you can take over all the endowment and then redistribute it. You can actually change distribution at will here, okay? So there is something called the second wealth fundamental theorem of welfare economics that basically tells you a kind of inverse problem related to optimality of the system. So for any Pareto optimal levels of utility, okay, so you know the profile of utilities of the society, there are transfers of the numerical commodity. So imagine these are taxes, right, that add up to zero. So that is lump sum transfers, such that a competitive equilibrium reached from endowment, so omega m plus T1 plus omega ni plus Ti yields precisely the utilities U1 to Ui prime. So basically these utilities are experience utilities. So that means let's say you want to reach a particular profile of individual utilities in this frontier of Pareto utilities. So all of these allocations alone are a max of this problem of the aggregate surplus. But each of them involve different distributions of utilities. So in each of them, for instance, you can have very extreme allocations where some individuals are super rich in a sense, a lot of consumption, others don't consume much. So basically you can move in this frontier by means of redistribution of endowments. So this is the engineering problem, right? And basically, it means that the government can come, take all the endowment, the physical goods in this economy, and then basically that means put an income tax that takes away all the money, and then redistribute it at will. But then you don't touch the market itself of the consumption good, because you still let the people do what they're doing, and then they are going to be maximizing profits, maximizing utility, given their new endowments, which is the summation of the omega plus ti. So now, what is the important thing here? So notice that this allows me to move basically inequality to whatever level I want without messing with efficiency of the market system, okay? So I'm letting people still maximize utility subject to the new endowment and, given the price that it comes through the market. And then firms are still maximize profit, right? Given the new allocation of endowments. And now there is basically a new price. And these allocations are still Pareto optimal, but it will entail a very different distribution of welfare, okay? And now, so basically as an illustration of this point, so you can, this is an easy way to understand this. So imagine, for instance, that I have two consumers, okay? And then I have, this is the consumption of individual 1 and the consumption of individual 2. And then according to their utilities, I have this, this basically Pareto frontier that is telling me, this profile or basically the total amount of utilities of each of these two guys. So this means basically that this guy, individual 2, consumes nothing, but individual 1 consumes everything of the good, okay? And this point here, and this is basically the aggregate supply, all aggregate surplus, all of them are Pareto frontier. So nothing here is feasible, okay? Is not feasible. And everything here is feasible, but is not Pareto, okay? Is not Pareto. So all the points here on the line are in the Pareto frontier. These are all points that are Pareto optimal. So by changing endowments, basically the omega m of 1 and 2, I can move in this position. I can move in this frontier. For instance, reaching this point that is 45 degrees, right? Which basically tell you this is perfect equality of welfare. All of them entail, the same level of Pareto optimality. So in particular, the only difference that they have is the level of inequality. So this is the engineering problem. So by redistributing the endowment, I can reach any profile of utility, experience utility that I want using the market. Okay, so thank you. That's all for today.